Okay, this is one of my worst jokes, but variance is what any two statisticians are at. Okay, that was kind of pushing it. Now, this is a really cool applet that's on GeoGebra that's going to let me explore a more powerful way to measure spread than IQR. So first of all, these are some data points that I have here, and we've taken the average or the mean, and that's 1.4. And the cool thing is, if I move the data point, you can see how this is dragging the mean lower as I pull it further away from the group, right? So basically, if I wanted to look at the spread of the data, one thing I could do is look at all these numbers here. Now, this is E is 4.6 above the mean, D is 2.6, C is 1.6 above the mean. A and B are both below the means. And you can see this should show a negative, but the software is a little picky and it's showing the negative here. So these are below the means. So these are called the deviations, which is the distance from the point to the mean. I can't really use the total deviation because that's zero. And zero is not going to tell me a lot about the spread. If I move the point, it's still zero. Even if I bring these over this way, it never changes from zero. So I don't want to use that point. I don't want to use just the deviation. So how can I make this not add up to zero? I could square them. So we're going to go ahead and take a look at the following data set with the points -4, -2, 3, 4, and 6, which is listed right here in the table. The first thing we need to know is if we're going to find the deviation, we need to know how far the point is from the mean. So the mean is just adding up all those points and dividing by 5, which is 1.4. So to find the deviation here, it's x minus x bar, where x bar stands for the mean. -4 minus 1.4 is -5.4. -2 minus 1.4 is -3.4. 3 minus 1.4 is 1.6. 4 minus 1.4 is 2.6. 6 minus 1.4 is 4.6. And again, if I were to actually add up all these values, I would get 0. Now, that means I want to do something to make it so we can get rid of this 0, and we're going to square the deviation so we get rid of the negatives. When we square the deviations, which is right here, -5.4 squared is 29.16. We get 11.56, and I square the rest of the numbers, and I add them up, 71.20. Now, this number here, if I add more data points, this number is really kind of just going to keep growing. So it's not really fair to compare spread on a small set of data compared to a large set of data. How can we make that more fair? Well, we could divide by n. So that would give us the average squared deviation. Now, this is only for populations. We actually make an adjustment for samples, so pay attention. So if I take this 71.20 and divide by 5, I get 14.24, 14.2. Then I'm going to take the square root to get us back into the units, because 14.2, even though it makes a little bit more sense with this set of data, it's still big. And the reason is because it's squared. How do we fix that? We take the square root, and the square root of 14.24 is 3.77, which makes a lot more sense if I'm trying to describe the spread of these points right here. Now, for samples, if we don't have the entire population, we divide by n minus 1 instead of n. So instead of dividing by 5, very important to note here, I am actually dividing by 4, not by 5. So for samples, you divide by n minus 1, all right? And my standard deviation in this calculation is 4.22. So what geometry theorem does this remind you of? It's not really required, although it's going to come up a little later, the Pythagorean theorem. Let's go ahead and do an example. Here are the measurements of the level of phosphate in the blood of a patient in milligrams per deciliter of blood. This is made on 6 consecutive visits, so I have 6 data points right here. we want to determine the mean and the standard deviation. When I add these all up, I get 32.4, and there's 6 data points. So divide the 32.4 by 6, and I get 5.4. That's the mean value. 5.6 minus 5.4 is 0.2. 5.2 minus 5.4 is actually negative 0.2. And here are the rest of the differences or deviations. Again, when I add these up, I get 0 when I just have a list of data. So we're going to go ahead and square these and add them up like we did before. Now, this is a sample, not a population. So instead of dividing by 6, which is a number of data points, I'm going to divide by 6 minus 1, or 5. And my variance in this case is 0.412. My standard deviation is the square root of that, which is 0.642. Now, if you look at the math chart, variance for a sample is denoted by S squared. Standard deviation for a sample is just S. And that is the formula x minus x bar all over n minus 1, which is the one you're normally going to use. If by some chance you happen to have the entire population instead, it's actually sigma squared for variance, and the standard deviation is called sigma. And the formula is x minus mu because I have the population parameter instead of just the sample statistic, and I'm dividing by n for the population. This symbol right here means sum of, so I have to add these all up, which shows pretty well when I use a table. Now, the coefficient of variation is one way to determine if spread is wider than expected. We're just going to compare it to the average. How do we do that? We're going to take our standard deviation value and divide by x bar and multiply it by 100%. A coefficient of variation does not have units, and it's usually just done in percent. Now, another cool theorem we run into is called Chebyshev's theorem, and it comes from this proportion, 1 minus 1 over k squared, where k stands for the number of standard deviations. Well, what Chebyshev found is if you put in, say you were 1 standard deviation away, 1 minus 1 over 1, that's 0. So 0% of the data is guaranteed to be within 1 standard deviation. If you're within 2 standard deviations away, 1 minus 1 over 2 squared, 1 minus 1/4 is 3/4. He said 3/4, or 75% of the data, falls within 2 standard deviations of the mean. So it's a band that's 2 standard deviations wide with the mean in the middle. So if we're going left to right, presume this is a small side for you, from the minimum to the mean is 2 standard deviations, and not the true minimum, but this band that we're creating. And then you add another 2 standard deviations to the mean, and if you create this window, 2 standard deviations on either side of the mean, you will capture 75% of the data points. If you substitute 3 in here, you're going to find that 8/9 of the data falls within 3 standard deviations, or 88.9%. So we're going to revisit both of these things with our previous example. I do want to show you the computational formula for standard deviation. So that can be a shortcut at times where you don't actually have to subtract. I could show you a very fancy derivation of it, but most of you really aren't into that right now. So this formula uses the sum of x squared, the sum of x's, which we then square, uses n and n minus 1. You already know that n is just the number of data points. N minus 1 is 1 less than that. So the sum of x, we just add these up. Then we square the x's, and we add those up. And then we substitute them in this formula, 177.02 minus 32.4 squared over 6 divided by 5. And we get that the variance is 0.412, and the standard deviation is 0.64. So what is the coefficient of variation in this sample? Well, I need the standard deviation, and I also need the mean. And the coefficient of variation is S over x bar, 0.64 over 5.4, and you multiply that by 100%, and you get 0.199, or 11.9%. Now the next bit is we're going to create these bands where we're going to capture 75% of the data, and that's that 3/4 right there. So we want to capture 75% of the data, and for the other one we're going to do 8/9 of the data. Well, recall that for 75% of the data, 3/4 of the data falls within 2 standard deviations of the mean. So first of all, I need to know the standard deviation is 0.64, which we had before. I'm going to double that, and I get 1.28. So if I go 2 standard deviations below the 5.4, how far down will I go? Well, 5.4 minus 1.28 is 4.12. So that will be on the lower edge of my band. If I want to figure out the upper band, I go 2 standard deviations above the mean there, and I'm going to add 1.28 to 5.4, so I get 6.68. Now with 8/9, all we're dealing with instead is 3 standard deviations of the mean instead of 2. So instead of 2 times 0.64, I have 3 times 0.64, and I get 1.92. To figure the lower band, I subtract that from the mean, and to find the upper band, I add that to the mean. So 8/9 of my data will fall within 3.48 and 7.32. Now there's a very nice applet you can use so you don't have to calculate standard deviation by hand, and it's at Staplet, and it's a one quantitative variable single group, and you've used it before when we've done dot plots and histograms. So basically go to the same applet, and there's a link. Type in your name right here. So in our example, the label would have been phosphate levels. If using a list of data, make sure that the raw data is selected right here, and then put in your data, and you can separate it with commas or spaces, and then you just click on Begin Analysis below the data. So what it'll generate is it'll typically generate a dot plot, but what we're really interested in here is the summary statistics, and those are in the table below the graph. N is just a number of data points that you entered. The mean is the average of all those data points, and there's the standard deviation, which we just learned about. And the min is the minimum value, mead is the median value, and max is the maximum value of the data set. Anyways, now we're going to go ahead and look at 2 things, sources of variability and actually also transforming data. So sources of variability. An instrument is something that we use to take measurements of data. They can take different forms, including surveys, scales, meters of various types, visual to determine color, and rulers. I actually personally worked in analytical instrumentation back after college. And the meters that we used, they were actually quite expensive, like $20,000, $30,000. Online ones could go up to $300,000. And we sold them all around the world to measure different things. And one of my jobs, let's say if I was selling one to measure sulfur in diesel, which was one of our big markets, I would take a sample of diesel and put it in the instrument and measure it 10 times and report the average and the standard deviation and compare it to what it was actually supposed to be. And the reason is instruments sometimes have error and they vary naturally. So measurement variability explains differences in our results. So they can result from a lack of precision in the instrumentation, like I described before, or differences in how 2 different people read the measurement. So there are some measurements that we take by eyeball, or even if we're trying to use a ruler, sometimes we're not quite sure which marking we want to go to. When we take samples or measurements, we're trying to estimate the parameter, the actual value, using the statistic. So if we measure the heights of students in a classroom, if I measured one student multiple times, you wouldn't expect a lot of variability there. But if I measured the heights of all the students in one class, I know I have one class where 6'3", my tallest student is that tall, and the shortest is probably like 5'2". Is that because I'm making errors in measurement? No, that's called natural variability. And there's just some natural variation between us. So at the beginning of our year, we actually did this little thing called random rectangles, where we were trying to estimate the parameter for the average area of the population of rectangles. And we did it, and initially I had you guys do just like a really quick guess. And the top graph here shows the spread of the data. So you can see, not so good when you had only 20, 30 seconds to look. Then we had you use your judgment and average 5 rectangles. Then we used randomness to pick 5 rectangles. And we found that when we use randomness, that gets rid of our biases, in this case towards larger rectangles. And we still have some variation. So this is called sample variability, and that's due to the randomness of the sampling process. Why do we stick with the randomness? Because on average, we do better when we eliminate biases and we use randomness in sampling and other things like experiments. So in experiments, we want to introduce variability so we can determine causal relationships. This is called induced variability. And the way we do it is we randomly assign different treatments to the experimental subjects. We don't let them choose and we don't choose. We just let randomness guide. So one last thing that we're going to look at is the effect of transforming data. So first we're going to start with some of the 2017 Texas A&M football players. Here are their actual weights. And I'm going to determine some statistics for them, including the mean, the median, range, and standard deviation for their original weights. So I can go to Applet and enter in quantitative variable, single group. Variable name is football weights. All right. And then I can just put in the data separated by commas. So you have the 185, the 202. When I'm done, I'm going to click on Begin Analysis. And then you can see all of my statistics right there. So there they are. Here we're just going to look at the mean, which is a measure of position, 230.25. The median is also a measure of position, and that one is down here where it splits the data in half. The range is 120. Notice that's not a position. That's a measure of spread. And standard deviation is only 39.34. That's also not a position. That's just a measure of spread. So now we're going to say that the coach puts them on a diet because they're going to France, and he wants them to lose exactly 5 pounds. And let's pretend they can all lose exactly 5 pounds. So I'm going to just subtract 5 pounds from both of those, and I already did it here. And I'm going to put my new set of data into the Applet. They do have a cool thing where you can do multiple groups, and so I'll put my football weights in there again. And here's my original data, which I pasted in, and now I'll type in my new data. When I'm done, I'll click on Begin Analysis. And you can see both dot plots in all the statistics. So if you look at the dot plots, you can see that they look almost the same. There's just a shift. Why is there a shift? Because everybody lost 5 pounds. Now, what did it do to the stats? My mean went down and my median went down by 5 pounds. Well, what about my standard deviation? My spread looks like it's the same. How about range? Well, we can go ahead and calculate the new range, which is 300 minus 180. It's still the same, which makes sense because the spread on these dots seems to be, hasn't changed. All right, so they fly to France and they get their weight reported in kilograms. One way you can change pounds to kilograms is dividing by 2.205. So let's go ahead and do that. And we'll put our new set of data in. So cool thing is I can just edit inputs and add another group. And now we're doing kilogram weight. And I pasted that in, and you can begin the analysis. So you can see the table with all the numbers on bottom. But what's also interesting to look at is when you go from lose 5 pounds to kilograms, there's a big difference in both those dot plots. Kilograms is much tighter. It's almost as if I had divided, I made it smaller by dividing. So what happens? My new range is 54.43, and all my stats were divided by 2.205. You can see the mean is like cut in half, so is the standard deviation, so is the median, so is the max, and so is the min. But since they're cut in half, the range is also smaller. It's cut in half, which kind of makes sense. The spread here looks like it's about half as big as the spread in pounds. All right, so they have a great time in France and they gain 5 kilograms because of all the croissants and everything else. So here are their new weights. All right, and we'll put this set of data into applet. So I'll go to edit inputs again, add a new group where they heavier, 5 kilogram heavier football players, put in my data, and you can see the stats. So what's going on now is this is just a shift. So when I'm comparing from here to here, sure, anything in position is changing because it's shifting, but the spread is about the same. You can see the standard deviation is the same there. So that's the only measure of spread really that's in this table. Okay, so my mean and median went up, and my range actually stayed the same because my min and my max went up by the same amount. And that makes sense because range is a measure of spread. It's just not in that table. And standard deviation also stays the same because it's a measure of spread. Okay, finally, they're coming back to the US, and we're going to convert their weights back to pounds, which we can do by undoing the division, and now we're doing multiplication. So here are their new weights in pounds, and we want to go ahead and look at this set of data. And so I edit my inputs, add another group, which is convert to pounds, put in my data, begin analysis, and you can see that the dot plot has shifted all the way over to the right again because I multiplied all these data points by roughly 2, and it has double the spread. So it should be that everything is changing. See how the standard deviation changed there? All these other numbers changed. And when I calculate the range, instead of the 54, it's now the 120. So to summarize, here are the dot plots again. When you add or subtract, all dots shift, but the distances between them, which is the spread of the variability, doesn't change. But when you multiply or divide, that changes the whole scale, and that's going to affect both location and spread. So it's a nice summary for you if you're trying to figure out what to do. If you're dealing with a measure of position like mean, median, min, max, and you're adding or subtracting a constant, just do that to all of those stats, all right? If you're multiplying or dividing by a constant, you should also do that because it affects these. So measure of position is affected by everything. Now measures of spread, so far we've learned standard deviation and range. Well, when we add or subtract by a constant, we notice that there was no effect on the range or the standard deviation. But when we multiply or divide, we did see an effect. So any factors that are multiplying or dividing, they will affect any measures of spread, like the standard deviation and the range.